So last time, we solved a differential equation like this, a system of differential equations expressed in matrix form, and we solved it, given an initial condition, by basically good luck. A lucky whisper told us a change of coordinates. Given that nice change of variables that was given to us, we just substituted in, found that we had scalar differential equations, proceeded to solve the scalar differential equations, and put the result together and got the solution. So what we're going to talk about now is how can we possibly find this nice thing, this nice change of variables, without having to have someone whisper it to us. Basically, how can we get the computer to whisper it to us? So to do that, we're going to have to step back and maybe look at this using a little bit more general language, just so we can see the big picture of what we're trying to do. So when you look at differential equations like this, we'll view them instead using letters, just to make our life easier, using d by dt x of t. And instead of this matrix, we're just going to call it an A matrix. A x of t, and there's going to be some initial condition, x of 0 is some x naught. We would like to solve these things. So what we need to do here is to understand at a pictorial level what we're talking about. Essentially, we're going to have to think about change of variables. To think about change of variables, we need to understand how to represent changes of variables using a picture, and then that will help us reason about them. So what we're going to do is we're going to think about two different sets of coordinates. We're going to think about native x coordinates. So these are the coordinates that x naturally lives in. Okay? So suppose these coordinates are over here. We're going to think about some other nice coordinates. So nice, call them x tilde coordinates. And they'll live over here. So the idea is that we want to think about a change of variables from x to x tilde, and so we're going to see this way. So what we're going to do is we're going to view these changes of variables and represent them using matrices. If we have a vector that we can represent in x tilde coordinates, we're going to think about a matrix V that takes us from these coordinates back to the original. Similarly, we can go the other way using V inverse. So far, so good. This is the basic story of how we go between these two coordinate systems. Now, in the native x coordinates, we have a differential equation, something like this. And this differential equation tells us how to relate the variable to its derivatives. And we know there's a linear transformation that maps the variable to its derivative, and that transformation is given by A. So the same way, this A defines the differential equation, the system of differential equations. In the same way, there's going to be some transformation that takes the x tilde coordinates from the variables to their derivatives. That's the new differential equation we got. So you notice last time we got a nice upper triangular form. So this matrix we'd like to have a nice form. So it's good to remember this, at the end of the day, is the same coordinate system down here. It's the same coordinate system up here. So we can always go from here up there using V. We can always go down using V inverse. So then the question is, what goes in this box? So we want to think about d by dt x tilde of t equals something times x tilde of t. So what is this thing? How can we figure out what that is? So to understand what goes in here, we can simply follow things through. So we say, okay, d by dt x tilde of t. This is just d by dt of the inverse x of t. Why? Because what is x tilde? X tilde is just v inverse x. which is just v inverse d by dt x of t, which is v inverse a x of t. But what is x? X is just v times x tilde. Remember, that's how we go back and forth. V inverse a v x tilde t. So what goes in this box? This goes in this box. So this is a way of understanding how, given a particular differential equation in one set of coordinates, how we can get a differential equation in a different set of coordinates. Tell me how to go from those coordinates back to these coordinates, or alternatively, tell me how to go from the original coordinates to the new coordinates. Tell me the change of variables. Then I can figure out what this is. We did this before, but let me describe another way of thinking about this diagram that helps us see what this is. So remember, when we think about vectors and matrices in this course, we generally use column vectors. And column vectors are acted on by matrices in that you multiply the column vector from the left by a particular matrix. So if you want to go from here to here, one way of going from here to here is to first go up by v. So take whatever you have, multiply by v, then multiply that by a, then multiply that by v inverse. So we write this as v, a, v inverse, just because of the way that we compose matrix multiplication. So saying this is v inverse av is the same as saying to go from here to here, we can go v, a, v inverse. So sometimes students get confused because this order seems reversed. We just have to remember which order we do matrix multiplication. That's because in this course we use columns as our default for vectors, and so the matrix multiplication works out in this kind of seemingly backwards order to some people. But it's pretty clear if you think about what everything means. So now we know how we can go between coordinate systems. Now these kind of diagrams are invaluable to understand what is going on. So to understand what's going on, we would like to find a coordinate system v inverse a such that v inverse av is a nice matrix. So we want this to be nice. Now nice isn't a technical term, so what do we mean by this? Like upper triangular would be great. Why would upper triangular be good? Because if this matrix were upper triangular, then at the bottom here, we would get a scalar differential equation. Having gotten that scalar differential equation, we could solve it and treat this as an input to the previous differential equation and keep going. So that's good. What's the simplest kind of upper triangular matrix? Simplest kind of upper triangular matrix is one in which we don't even have to do the back substitution, where the matrix is simply diagonal. So upper triangular would be good, and diagonal, would be great. Because here we have to do back substitution, and here no back substitution needed. We'll find this course we can't always get away without having to do back substitution, but sometimes we can. So let's think. We might as well dream for the best, right? Hope for the best. Let's see if we can get a diagonal. So how can we possibly get something to be diagonal? That's really the question. So to understand this better, we need to step a little bit back and think back to what do changes of coordinates really mean, right? So what changes of coordinates mean, so let's go back temporarily to 16a, where you first learned about vectors and matrices. So in 16a, when you started off in module 1, you had this problem of imaging. And so in imaging, what were the two kinds of coordinates you had? Well, the two kinds of coordinates you had were native pixel coordinates and the measured voltage coordinates. Remember, in 16a lab, what you did was you had a single pixel camera, which is that you had the ability to shine light in a particular pattern onto an image and measure the total intensity by measuring the voltage on a particular photodetector. So you had these two different sets of coordinates. And what connected them? Well, the measurement mask, M, connected the native pixel coordinates to the measured voltage coordinates. What do I mean by that? By that I mean that it was the rows of M that told you how that particular measurement related to the original pixels in the image. And similarly, you could use M inverse to go back. So native pixel coordinates, so you think about X as being up here. How do you think about X? X up here was represented, if you had A, B, C, and so on. What does this A represent? A was the intensity of the first pixel. And B was the intensity of the second pixel, and so on. And what were the measured voltage coordinates? So let's call them x tilde over here. In this, A prime, B prime, and so on, A prime is the first measurement result. And this thing was some sum, right? A prime was some sum over I of the measurement matrix first row, ith column of whatever x was, whatever the underlying image was, indexed into the ith position. So this is what is meant by M transforming x, the image, into these new coordinates, which are the measured voltages. So, and this is written in 16a by saying x tilde equals M times x. So this is the idea of what we mean by changes of coordinates. Now, what's useful here, this is the way you're used to thinking about it in 16a. Notice here, I've drawn it with a different set of notations. There you thought of the measurement matrix is what gave you the measurements you had, and then you can use the inverse of the measurement matrix to get back the pixels. Here I used V without an inverse to represent the backwards path. Why did I do that? I did that because I wanted this V to have a particular meaning. So what is it that I want this V to mean? So what is it I want V to be? So V is a matrix, but it's actually composed of vectors inside of it. There's V1, there's V2, there's V3, and so on. Lots of V's. Say there's n of them. I want to think about these vectors as meaning something. These vectors tell me how I can view something that's in x tilde coordinates back in x coordinates. So when I say that x equals v times x tilde, what I'm really saying is that x is equal to the sum, I equals 1 to n, of x tilde indexed into the ith position times vi. So this should remind you of something. This should remind you from 16a of writing something in a particular basis. So the vector x can be thought of here as being the sum of these x tildes times the vi. So we can view these nice x tilde coordinates. These are these coordinates we can view as being in the basis. When I say that these coordinates are in V basis, I mean that in order to interpret these coordinates in terms of whatever physical thing you're talking about, you need to use the V basis to go back to the native basis, whatever it is. So we're looking for, when we say we're looking for a nice coordinate system, what we're looking for is a nice basis. So when you want to do a change of variables, what we're trying to do is find a nice basis. What makes a basis nice? What makes a basis nice is that the matrix we're interested in particular the A matrix, is represented nicely in these coordinates. So what is this matrix, this linear operation, look like in V coordinates, in the V basis? It looks like V inverse AV. We want V inverse AV to be nice. Nice meaning upper triangular or diagonal. So now let's think about what does it take for this to be nice. So for this, we have to think back to what we're looking for in this differential equation. What makes a basis nice? Nice what? Nice relative to transformation A. What we're looking for is a way to get things so that in the changed coordinates, the problem decomposes into some kind of scalar problems. So it would be wonderful if we had a vector v1 so that when we wrote out x tilde, if x tilde was just a scalar, a single scalar function of time, and we treated the vector x tilde as just being x tilde of t times v1, it would be great if when we had A acting on this, right, so A acting on x tilde of t v1, which is, remember, this is a scalar, so this is just x tilde of t a v1. It would be wonderful if a v1 was in the same direction as v1. Why would that be great? Because if a v1 was just equal to lambda v1, then I would get a scalar differential equation. Why would that? Why? Because then d by dt of x tilde of t v1 would just equal lambda x tilde of t v1, which is just saying that the derivative is just in the same direction as v1, and so this is basically a scalar differential equation. So if I can find vectors v1 such that the matrix acts on those vectors as though they were simply a scalar multiplication, then it would be great. But we have seen this kind of thing before. In 16a, you learned that when you have a matrix and you find a vector v such that this is just equal to some scalar times that same vector, then this is called an eigenvalue of A, and v1 is the corresponding eigenvector. So this ability of basically having, this ability of having everything be decomposing into scalars, to scalar differential equations, is tied to eigenvalue and eigenvectors somehow. So let's see how this works out. Why does this work out? So this gives us a guess. So far, this is like a thought. So it gives us a guess that if I had v equaling v1, v2, vn, where v1, v2, vn were, of course, linearly independent, because they need a basis. And each was an eigenvector of A, namely A vi equals lambda I vi, then we would be in good shape. So this says if I can find a bunch of eigenvectors that form a basis, that might be a very nice coordinate system to look at. Now, why would that be the case? So let's see. Do we believe this? Why should we believe this? So the interesting quantity for us is to look at V inverse AV. We would like this matrix to be nice. So what does this look like if V is a bunch of eigenvectors? So this is equal to V inverse A, V1, V2, Vn. So now we recall from 16a, what does matrix multiplication mean? When you multiply a matrix by another matrix, what you're really doing is taking every column in the second matrix and multiplying it by the first matrix, and then taking the matrix that consists of those columns, one after the other. So this is just equal to V inverse and the matrix of A V1, A V2, all the way up to A Vn. But we said that each of these V's is an eigenvector. So all of these, this is just equaling V inverse times the matrix lambda 1 v1, lambda 2 v2, all the way up to lambda n vn. So far, so good. So now, what happens next? We want to understand what is V inverse times these. So we have to ask ourselves, aside, what is V inverse times VI? Well, we know that V inverse times V is the identity. That's what it means for it to be, an inverse. So if V inverse times V is the identity, that means we know V inverse times V1, V2, all the way up to Vn equals the identity. But if we want to know what V inverse times any one of these is, we just have to look at the appropriate column of the identity. So this is just the first column of the identity times lambda 1. The second column of the identity times lambda 2. The third column of the identity times lambda 3. And so on, all the way to the last column of the identity times lambda n. So this is a diagonal matrix. With the eigenvalues on the diagonal. So that tells us that if we can compute the eigenvalues and eigenvectors of a matrix, we can find a vector v that represents a change of coordinates such that the matrix A we're interested in, so we find all the eigenvectors and eigenvalues. If we have a full set, we can take that change of coordinates and we will get a diagonal matrix. So let's write down that fact for ourselves. Oops. Call such V's an eigenbasis. What's an eigenbasis? Eigenbasis is a basis of eigenvectors. If V is an eigenbasis, then A transformed into this basis, which is V inverse AV, is equal to a diagonal matrix of eigenvalues. I'll write zeros here to mean everything else is zero. So that means what in the context of our problem? So our problem here says that the differential equation, the system of differential equations that govern x tilde as a vector, is governed by this matrix. But that's diagonal, which means so d by dt x tilde of t, this differential equation is just that diagonal matrix times this vector. This is just a collection of scalar differential equations. And because it's a collection of scalar equations, we can solve it. So that tells us, now we know how we can find a coordinate system that is particularly nice for us. Next time, we'll just work out this particular example to see how that works.